All right, we're going to do a couple of application problems in this section. Vectors are everywhere. Displacement, velocity, and acceleration are all vector quantities, as is force and tension. So you see vectors, vector applications a whole lot in physics. We're going to do a couple of examples in this section. Well, we'll start here. This is a velocity problem. So a ship's navigator determines that a ship is moving through the water, so that's like in reference to the water, at 28.2 kilometers per hour with a heading of 26.3 degrees north of east, but that the ship is actually moving at 31.1 kilometers per hour in a direction of 33.7 degrees north of east. And we want to know what is the velocity of the current. So overall, basically, what's contributing to the total velocity of the ship is how it moves through the water, but then also how the water is moving, right? And sort of those together give the overall velocity of the ship. They give us these directions in reference to saying that it's north of east, and as it turns out, north of east is our standard position if we put our compass directions in the standard spots, right? North, south, east, and west. Then north of east just means up from the positive x-axis. So they gave us the standard position angles here. Let's see. I'm going to start by labeling some vectors. So I'll let VC be the velocity of the current. VS will be the velocity of the ship through the water. And VT will be the total velocity. And the overall relationship between these vectors is that the total velocity is the sum, is the resultant of the velocity of the current and the velocity of the ship through the water. They gave us the velocity of the ship through the water. They gave us the total velocity. What we want is the velocity of the current. So that's our goal. And so I'm going to take this equation. Here we have an addition of vectors equation, but we want to solve for the velocity of the current. So algebraically, we could just subtract these VS from both sides. So we get that VT minus VS is equal to VC. And that's what we're going to use. We can subtract vectors just like we add them. It's just that when we find the components, we'll subtract the x components to get the x component and subtract the y components to get the y component. So let's begin by finding these components. So VC is VT minus VS, so maybe I'll find VT first. And they said that VT is that it's actually moving at 31.1 kilometers per hour at 33.7 degrees. So 31.1 at 33.7 degrees. So VTX be magnitude times cosine. And that's 25.87. And VTY is magnitude times sine. Oops, sine 33.7. So that is 17.26. Okay. Now we'll do the same for VS. Vs is, I'm going to scroll up again just to get that information. Let's see, it's moving through the water at 28.2 with at a heading of 26.3 degrees north of east. So 28.2 at 26.3 degrees. So Vsx magnitude times cosine. That gives us 25.28. And the y component will be 28.2 times sine of 26.3 degrees. And that's 12.49. Okay, so now that we have these components, we can find the velocity of the current. We can get the components for the velocity of the current. So this relationship up here, right, so we kind of figured out how the velocity of the current is related to the velocity, the total velocity and the velocity of the ship through the water. So that applies to the components. So Vcx is equal to Vtx minus Vsx, and Vcy is equal to Vty minus Vsy. So we're just going to subtract these components. So for the x component, 25.87 minus 25.28 is 0.59, and Vcy, that'll be 17.26 minus 12.49. And that's 4.77. Now we have our components. They're both positive components, so this will be a first quadrant vector. We'll get our magnitude with Pythagoras as usual. Oops. Uh, 4.81 and the so the magnitude adopts the units of the original vector, so that's kilometers per hour, and in fact that's true for the components too. We could have put units on those components and they would be in kilometers per hour. It's a first quadrant vector, so we don't have to make any adjustments. It's just arctan of the y component divided by the x component (82.9 degrees). And putting this together, the velocity of the current is 4.81 kilometers per hour at 82.9 degrees. All right, so one more example, and this is an example that occurs a lot in physics. A lot of application problems in physics involve a system that is in equilibrium. So there might be some forces or tensions acting on an object that's in equilibrium. Something's in equilibrium if it's not moving. And the way that happens, if something is not actually in motion, it means that the forces acting on it must be equal and opposite. So like the sum of the x components is 0 and the sum of the y components is 0. So in this example, we have a 225 kilogram sign supported by a cable. So the sign is just hanging there. It is not moving. We know that it says it's a 225 kilogram sign. So we know that the sign is exerting 225 kilograms downward. That's its mass. And now we have this cable that's exerting a tension, right? So there's this tension in this cable that's holding the sign up. And we know that that tension has to be acting in such a way that that the system is in equilibrium. So what I'm going to do first, I'm actually going to sketch out these vectors on the plane. So here's the sign. That is 225 kilograms, straight down. Here's the tension. Now this tension is at 40 degrees this way, which means that it's the direction of that vector, being a second quadrant angle, is 140 degrees. And this vector has some components, tx and ty. Now we know, because the sign is exerting a force straight down at 225 kilograms, that ty has to be 225. And that's the relationship that we're going to use. So since the sign is exerting 225 kilograms straight down, we know that ty has to be 225 kilograms positive, straight up. We also know that ty is given by the magnitude times sine of theta. And so this is, we get 225 kilograms is equal to the magnitude times sine of 140 degrees. And this is what's going to allow us to find the magnitude of that tension, which is what we're after, right? They asked us to find the tension in the cable. We already know the direction, so that means we just need to find the magnitude. And we'll do that just by dividing both sides by sine of 140 degrees. So 225 divided by sine of 140 is 350.04 kilograms. And so this tension in the cable is 350.04 kilograms at an angle of 140 degrees.